Hello, my name is Kola Olutman, and I'm here today to discuss an interesting problem set related to fundamental data structure, specifically finding the intersection and union of two sets without relying on built-in method. This stimulates a common technical interface, and I'm ready to walk you through each approach of the work. Let's begin with describing how I will write a function to find the intersection of the two sets. My overall approach for finding the intersection sets of set A and set B is to iterate effectively through one set and check for element presence in the other. I will leverage the fast lookup capability of a hash-based set data structure, like a hash set in C++ or a set in JavaScript or Python. This is step-by-step function and would look like this. I will start by initializing an empty result set. Let's call it intersection set. Then, for optimal performance, I would decide to iterate over the smaller of the two input sets. Let's assume set A is currently the smaller one. For each element item in set A, I will check if set B also contains that item. Number 4. If set B doesn't contain that item, meaning it exists in both, I will add item to our intersection set. Number 5. Once I've iterated through all the elements of the smaller set, intersection set will contain all the unique elements common for both. Regarding to big O performance, this approach is OMNM, where N is the set of set A and M is the set of set B. This is because we only iterate through elements of the smaller set and each contain operation on a hash-based set take on average constant time minus O1. Intersection test sets. To ensure this approach will work correctly, I would highlight at least 3 test cases. Standard intersection set A 1, 2, 3, 4, set B 3, 4, 5, 6, expected 3, 4. These tests typically overlapping elements. No intersection set A 1, 2, set B 3, 4, expected an empty set. This survives correct handling when there is no common element. Number 3, subset relationship. Set A 1, 2, 3, set B 1, 2, 3, 4, 5, expected 1, 2, 3. This checks scenario where one set is entirely contained within other. Transition to union. Now let's move on the second question, finding the union of two sets. Union approach, step big O. For the union of set A and set B, my strategy is simpler. I will just combine all the elements from both sets into a new hash-based set. The neutral behavior of a set that is only stored in unique elements will automatically undo any duplicate. Here's how the function would work step by step. Number 1, first, I will initialize an empty result set. Let's call it union set. Number 2, then I will iterate through each element item in set A, adding each item directly to union set. Number 3, next, I will iterate through each element in item in set B, again adding each item to union set. If an element from set B is already present in union set because it was also in set A, the add operation won't re-add it, maintaining on uniquences. Big O performance for finding the union is O into bracket n plus m, where the n is the number of the element in set A and m is the number of elements in set B, where we iterate through all elements of both sets and each addition to a hash-based set takes on average O1 time. Thus, the total time is directly proportional to the total number of elements in both sets. For testing, union test case. For testing the union test, I will consider these three cases. Standard union. Number one, standard union. Set A 1, 2, 3. Set B 3, 4, 5. Expected 1, 2, 3, 4, 5. This checks the typical scenario with some overlapping elements and correctly handled. No overlap. Set A 1, 2. Set B 3, 4. Expected 1, 2, 3, 4. This ensures the function combine completely distinct sets correctly. One set is empty. Set A 1, 2, 3. Set B empty. Expected 1, 2, 3. This verifies proper behavior when one of the input set has no element. So in conclusion of how I will approach defining the internation of the union set without beating, including the step-by-step big O performance and relevant that test case. Thank you for listening.